Okay, hello everyone. I'm happy to introduce our speaker, Dr. Ronnie Kamai from the Department of Structural Engineering, Ben Gurion University of the Negev. Ronnie completed her PhD at the University of California, Davis, in the Davis Department of Civil and Environmental Engineering, focusing on liquefaction-induced shear strain localization processes in layered soil profiles. Ronnie completed her postdoc at Pacific Earthquake Engineering Research Center, UC Berkeley. And Ronnie was awarded by numerous honor citations and awards, like American Rock Mechanics Association Award, Excellence in Geotechnical Engineering, the Geomechanical Group Exemplary Achievement Award, Israel Geological Society Peretz Grader Award, Suzanne Zlotowski Admission Award for Outstanding Students, and by fellowships and special grants like Fulbright Foundation, doctoral scholarships, and Fulbright West graduate fellowships. And Ronnie's research interests are seismic hazard analysis, site response, and soil mechanics. Please, Ronnie.
Thank you, Edwina. Hello, everyone. I need to, when I came back from 7 years in California 2 years ago, it was hard for me to switch and talk in Hebrew, but now it's harder to go back and talk in English, so it's probably going to take me 2 minutes, but I'm going to get into it. So the title is long. We're going to explain it step by step in a minute, and the reason it says only presenting, you'll see it also in a few slides. I'm going to present not only my postdoc, but the full project, which was really a community effort of between 30 and 50 people that took part in this really big and interesting project, and I was part of that, but I want to introduce the entire project and its contribution and not just my part. So I'm presenting the full thing, but of course I didn't do all the work. There's a lot more than one person can do. So first, the motivation. I don't need to write anything. Our motivation is that not to see more pictures like this, earthquake consequences. The common thing of course, each of one of these are from different earthquakes, different parts of the world. The common thing is lack of preparedness. Now, not necessarily that, I'm not here to blame, not necessarily someone did something wrong, but obviously they were not prepared. If the evaluation of the hazard was not well, or the building code, or some link on the way caused this structure to collapse, this structure to sink and tilt, the port, of course, completely not able to function. So we don't want to see this, and as engineers, so I'm coming from the engineering perspective, kind of linking in between. As engineers, of course, we don't want to see this. We want to be better prepared. So we want to be better prepared for earthquakes. We want to first understand what do we need to take into account. So when I talk about earthquakes, this is my structure and I want to design it properly for an earthquake. I need to think of where is the earthquake going to happen, on which fault, which magnitude, how much energy is going to be released, how fast does the fault move, the slip rate, the rupture size. How are these waves, once the fault ruptures and there's an earthquake, how are the waves going to propagate through the crust? The earth crust, of course, is very heterogeneous. There's different damping. There's lots of different effects. How am I really going to take all of these into account? There's so many parameters, so many sources of uncertainty in this process if I want to be able to model the entire thing. So I have a source, I have a path, I also have a site. How is my specific site going to respond? If I'm on rock, I'm going to get one ground motion. If I'm on soil, I'm going to get a different ground motion. And all these different components have a lot of uncertainty in them, and all of these different components have to be linked together to be able to answer the question of what is my structure going to feel and how should I design it? So there are generally, very generally speaking, two approaches. I can try and use the theoretical / numerical / physical approach and model a full 3D mesh of the entire crustal structure of my region and propagate waves through it, even with relatively high efforts and uncertainty of the structural of the structure of the crust, still there's a lot of questions. How much damping? How do the waves propagate? Where does the earthquake come from? So there's a lot, many parameters we don't really know in this full theoretical framework, which we either need to guess or give a number and try, do a sensitivity analysis or whatever. The other approach is the empirical approach, which says we can collect today tens of thousands, easily maybe hundreds of thousands, earthquake recordings from around the world and learn from them. Look at how have earthquakes response, how did that behave in the past in different magnitudes, different locations, different everything, and parameterize that to come up with a model. I call that it's called the empirical approach, meaning I'm going to count on existing observations and I'm going to build a model based on those observations from previous earthquakes. So I'm going to today focus on the empirical approach, specifically talk about one component in the entire empirical approach, which is called basically the equation that connects between the earthquake and the site is called the attenuation model, or today we call it ground motion prediction equation. I'm going to introduce that in a minute. I'm not trying to, you see I'm losing my words now, say that the theoretical approach is not good. They have to come, I believe they have to come hand in hand. We want to do both. We want to learn each other from each other and try and combine the knowledge we can get from both different approaches. But I'm going to focus on the empirical approach. The empirical approach says we have earthquake recordings, we can collect those from today very many different environments and sites and locations and magnitudes and learn from them. If I go almost 20, 30 years backwards, traditionally these equations were relatively simple. They were called attenuation models, in Hebrew, mishvaot nichut. This is just one example from Boer et al., Boer, Joyner, and Fumal, I believe, in 1993. And you can see it's mostly, this is what the model predicts. It's a function of magnitude and distance. It says that as I get closer to the earthquake source, I'm going to get higher ground motions, higher intensity of ground motions. And of course, as I increase in magnitude, I'm going to get higher ground motions, right? We all expect that. But they give it a functional form, a numerical form that says, this is how it's going to behave as a function of magnitude and distance. And that's called the attenuation model because it's basically, what it's mostly describing is the attenuation with distance, how the waves attenuate and we lose the energy. That's the meaning of the word attenuation as we get farther away from the earthquake source. But if we look at actual earthquake recordings, this is PGA, so the maximum recorded acceleration from as a function of distance. Okay, so it's similar to this, just in real data. All the blue dots are data from California, magnitudes only between 3 and 5, so that's all in California. The red dots are one specific event. This is one specific event recorded at very many different stations. Magnitude is 4.2. It's called 1045 because there are so many of them. And we can see that it attenuates. We can see that as we get closer, there's more energy, of course. But we can also see that at, for example, a distance of 60 or 70 kilometers, what's going to be my ground motion? Anything between 10 to the minus 4 and 10 to the minus 2. That's a difference in 2 orders of magnitude in one event, one distance, okay? There's no magnitude and distance scaling here. This is one event at one distance, a difference of 2 orders of magnitude in the response. So obviously, trying to build equations, engineering applications based on only magnitude and distance is not enough. So when we look deeper into the data, we can see that it actually depends on the mechanism. Is it a reverse fault or a normal fault? going to skip aftershocks. What happens at the site? If I'm on a soil site or a rock site, it's going to behave different. Am I above the hanging wall of the reverse fault or not? Is my rupture buried or not? Surprisingly, if it's buried, there's actually more energy. And do I have basin response? So there's many, many more components. And this scary function is not even the function. The actual, what today is called, the project is called the Next Generation Attenuation Models. And I'm going to explain a little bit why next generation. It sounds really, promising, but why it's called next generation. NGA, okay, so the NGA is the framework I took part in, and that's the big project I'm going to talk about. But really today we like to call those ground motion prediction equations. So because they describe a lot more than just the attenuation with distance, but all these different parameters. And the GMPE itself that I'm putting up here is not this. Each one of these little F's is a whole, a few rows of equations, right? So it's a very complicated and nasty looking equation, but it's trying to describe the dependence on magnitude and distance. Here's the dependence on mechanism. So this is, if it's a reverse, use this function. If it's a normal fault, you see the end, use this function. If it's an aftershock, use this function. This is the dependence on site-specific properties of where I'm going to build my structure. This entire ugly-looking piece, F4, is a function of many, many different geometry, different parameters of geometry of the fault because it describes the hanging wall effect. I'm going to talk a little bit more later about the hanging wall effect. It's interesting. Z-tor is the component that talks about, is my rupture buried or not? And then the last part also should be together with the site response. How deep is the sediment basin? So really, these GMPEs, and as we have more and more and more updates of these GMPs, they become longer and more complicated and uglier. But on the other hand, our computation power is almost endless, right? And we code it all up into either Fortran or MATLAB or whatever you want. We provide that with the paper, and everyone can run the GMP, even if it's not a really nice one-line equation. So the equation is more complicated because it tries to describe, maybe with higher accuracy, more physical components, physical parameters that actually do influence the response, and that's what we see from the data. So to summarize everything I just said, and a little bit more than that, the physical phenomena trying to model, theoretically or numerically model, everything that goes into the rupture itself, how it propagates through the crust, and what happens when it comes to the surface is very complex. We can try and do that, and we do that better and better with available numerical platforms today, but there's still a lot of uncertainty of parameters we just don't know. So instead of that, the empirical model comes to say, here's the data, just use it and learn from it, and there's so much data we can use today. But the downside with using an empirical approach is that in the entire range of data, there's still, let's say, ranges in the data that are holes. So for example, if I take away subduction zones, because we look at different tectonic settings differently, if I look at, for example, like California, it's called an active coastal region. In areas like that, we don't have very many recordings of large earthquakes. Or I'll give you a better example, because we're going to talk about hanging wall later. We don't have very many recordings on top of the hanging wall. Everyone knows what a hanging wall is. Reverse fault, there's the hanging wall and the footwall. Okay, the hanging wall above the fault. Usually there's a mountain here, not a lot of cities, and hence not very many instrumentation. We just don't have recordings. So it's hard to build a statistical regression on very few data. So we have to supplement that with simulation. So really what's nice about the NGA, the next generation models, is that they try to benefit from both worlds. They say, wherever we have data, we're going to use regression tools, pretty advanced, not just simple least squares, regression tools to learn from the data. Wherever we don't have data, we are going to supplement that with specific simulations to answer questions about that component that we don't know. from the data. And I'm going to talk about that a little bit further as we go along. So that's the idea of what makes this a bigger project that really has so many different collaborators and contributors, is that different people look at different components, and then at the end we bring it all together. So this big NGA project started at Pacific Earthquake Engineering Research Center. It's a really long word, PEER, we call it. It's a large multi-institutional research center located, the headquarters are at UC Berkeley, but there's really people from all over states, mostly Western United States. They started in 2003 with a 5-year grant. They published models. They were pretty successful. The USGS National Hazard Maps. So this is what the engineers eventually use, is the National Hazard Map. They go here, say, okay, what's the number I need, and that's what they pull into their analysis in very simplified way, what I just described. That was published in 2008. It was very successful. They got funding for the second phase, which was NGA West 2. NGA West 3 is already ongoing. NGA East has almost completed, and NGA subduction is also ongoing. So this NGA project, which just started as kind of, let's develop models for California, grew into a monster, you could say, of many, many people, which together, again, in a community effort, try and answer different questions and come out with products that are used in the by the USGS and really are used across the nation in the US and also worldwide. For example, the Israeli National Hazard Map uses one of the 5 models that was published in 2008. So really it's used worldwide in places that didn't develop specific localized GMPs of their own, like Israel. We'll talk about that at the very end. So today I'm going to talk a little bit more about NGA West 2. That's the second phase of the big next generation attenuation project. Published in 2014, 5 models. These are the different contributors. So there's about 30 people here. Some are about to or have retired, and some are young as me or postdocs. So really a wide range of people, different expertise. The really great thing about that was to sit around the table with seismologists, structural engineers, geotechnical engineers, and discuss all these things together and have to talk with the same terminology and solve problems together. So that was very interesting. And you can also see representation here from universities, Stanford, UCLA, UC Berkeley, UC Davis, government agencies like USGS, and private consulting companies. So really, people from very different backgrounds and interests kind of joined together to develop these models. So focusing on the NGA West 2 project, we start with a database. We have to collect the data. It's an empirical approach. We have to collect the data. The database has 21,000 recordings from about 600 earthquakes. Last one was Christchurch, 2011. Magnitude range between 3 and 7.9. So it's a very wide range of magnitudes, and you can see the distribution of magnitude and distance here. You can see that most of the data is between 10 and 100 kilometers. That's where most of, that just happens to be where most of the recordings are. Very few recordings very, very, very close to earthquake sources. There are few, so you can already guess that if I want to very specifically model the ground motion very close to a large earthquake, I'm not going to have a lot of data to base an empirical model on. I'm going to have to use other sources, and we use numerical simulations for that. Distance between almost 0 and 1,500 kilometers. Most of the data comes from Western North America, so California, Japan, Taiwan, and a few others. Each of these 21,335 recordings, records, which came in as a time history of earthquakes, like you see whenever an earthquake happens, added additional pieces of information. So we know, or even if we don't know, we evaluate, and that's not me, that's whoever was responsible on the database, that's why there's so many people. The magnitude, the strike and dip and width and size of the rupture, latitude, longitude, of course, mechanisms, stress drop. We know different measures of the distance to the site, to the epicenter, to the hypocenter, to the rupture. So we collect as much information as we can on every single recording, and it becomes a really big Excel file with all this information, so we can ask all the questions. How does this affect? How does that affect the response? So you want to collect as much information as you can, of course, about the site, what's the geology, what's the different geotechnical parameters of the site. Each of these single recordings goes through very, very consistent processing. It has to go through filtering and baseline correction and removing all types of biases and instrument correction. So there's a separate paper on the processing and the tree of how everything is done very consistently, very open, shkifut, transparent. Thank you. So the database, we know everything was processed the same way, so we can treat it the same way. At the end, after all this processing, we get from every single recording, we get the PGA, that's the just peak acceleration, the PGV, peak velocity, peak displacement. We can also, of course, measure other different measures of the time history, and we also get a response spectra. I believe you probably don't know what a response spectra is because it's a very engineering type of measure. So I'm going to 2 minutes explain what a response spectra is, because that's what engineers use to design structures. And then later I'll just keep on talking in terms of response spectra, but really you can just think about it as PGA. It doesn't matter too much to the top. So when we get an earthquake, as I said, we can compute the peak acceleration, the peak velocity, Arius intensity, the duration, and we can use these as intensity measures of the earthquake ground motion and talk about how different physical parameters affect that intensity measure. We can also compute the response spectra, which looks like this. So this is, these black lines are actually the design spectrum that the engineer will use to design the structure. So the way it's computed is we take a full, complex, multi-degrees of freedom structure, and not we, and structural engineers simplify that into a single degree of freedom structure, which is basically a mass on a spring. So everything is simplified into a mass on a spring, not in the actual analysis, but at least for this specific calculation of the response spectra. And then we take these masses, and each time we put it on a different spring. So if it's on a very short spring, it's going to behave very stiff and going to vibrate fast, have a high frequency or a short period. And if we put it on a very long spring, long pole or spring, it's going to vibrate a little bit more like that, have a longer period, right? So if we change the length of the spring or the stiffness of the spring, the mass is going to respond differently. It's going to have a different natural period. And that natural period is really how that mass wants to rotate if you just pull it and let go. And then we subject it to the exact same input motion. That's the time history that we recorded from the actual site. We subject that to the base. We record, or we compute, really. This is an analytical step. We compute the response of the mass, and then we take the peak value, and that becomes the response spectra. So if you have no idea what I just said, that's okay. You can just relate to that as the PGA. It doesn't really matter for the continuation of the top, and it's really one way to describe an earthquake. It's called a response spectra. So the products, the final products of this big NGA West 2 project, second phase of the NGA, are 5 GMPs, and they all have the first initials of the authors. So ASK14, BSSA14 is Boer, Stewart, Saihan, Atkinson, Campbell, Bazornia, Chu and Young's Idris. These are all very established researchers in everyone except me and Saihan. Everyone are very older and established researchers in this field. We were lucky enough to join as young postdocs, which were kind of really lucky enough to join in even as authors of the actual final GMP. And naturally, I'm going to focus a little bit more on ASK14 because I know it a little bit better, but the basic is kind of a similar thing. So if I look at these five different models, all of these are five, remember, nasty long equations of how is the actual ground going to respond under my structure as a function of the magnitude, the distance, the dip, the strike, the site factors, all of those, right? So you would expect if they all try to describe the same phenomena based on the same database of 20,000 recordings, they would probably look the same, right? So they do sometimes. If I look at magnitude 6 on rock, they look very similar. There are 5 lines here. These are the 5 different models. These are the 4, sorry, Idris is a little different, so it doesn't appear in all the comparisons. So 4 different models here. They're very similar. Why are they similar here and not so similar here? Wake-up call, sorry.
Site-specific.
Or in more general term, this is not site-specific, so basically it's the same parameters that came into all of these equations. But the reason why the answer is different is that here we had a lot of data. So we have a lot of data around magnitude 6, around 30 kilometers on rock. Lots of data, all the models look the same. Where we don't have a lot of data, or where the models have to extrapolate because we don't have a lot of data around magnitude 8 on soil, then they look different. And they look different because here each modeler had to make decisions, take their own call on how this should respond, how this should react under these conditions. So this is kind of the, sometimes when you talk about these equations, people will just say, oh, this is just a regression. You just click, you just run a regression, whatever you can do with Excel, and what's the big deal about it? That's okay. There's a lot of regression into it, that's right. The only place where you really need to make, engineers like to call it engineering judgment, sounds very impressive, is where you just don't have the data. So you have to decide, do I let my model do whatever it wants to do, or do I constrain it? Do I make it go, for example, flat here, because I believe this is what it needs to do, based on physical constraint, my physical understanding of the earthquake phenomena or wave propagation. So there is physics behind here, and there's a lot, and I'm going to look into specific components in this equation, actually to these specific components. So I'm going to show you just the base form, the magnitude scaling, so how it behaves with different magnitudes, and the distance scaling, how it behaves with different distances, and specific, I'm going to point at specific behaviors. And then there's the site response, which we'll see if we get to depending on time, and the hanging wall component. The reason I chose to talk about these two is that actually the magnitude and scaling distance, this component, is almost entirely based on data. We have data, we regress with very few constraints at the ends. The site response and the hanging wall, there's just not a lot of data where we want it. So there's 1D site response simulations that really supplement a lot of our understanding here, and there's big finite fault simulations that we use to constrain the behavior here. I believe most of you don't have a geotechnical background in soil mechanics, so I think I'm not going to talk too deeply into the site response and talk a little bit more about hanging wall. And that's going to show the highlights of the models. So if I talk about magnitude scaling, and now I'm showing only the results, the model prediction, right, the median model prediction. And this is comparing Abramson and Silva 2008 with the new update, Abramson, Silva, Kamai 2013, for a range of magnitudes from magnitude 3 to magnitude 8 at spectral acceleration of 0.2 seconds, but again, you can read this as PGA. It doesn't really matter right now. And at 3 different distances. So distance of 200 kilometers, 30 kilometers, and 1 kilometer. So of course, if I look at 200 kilometers, and if I try to focus only on the bold lines right now, not in the comparison to the previous version, if I look at 200 kilometers, obviously at magnitude 4, 200 kilometers, I'm not going to feel a lot, and the PGA, or the spectral acceleration, is very, very low. As we increase the magnitude, 200 kilometers from a magnitude 8, you're going to feel that. It's not very strong, but you're going to feel that it's a magnitude 8. 30 kilometers, you're going to feel more, and 1 kilometer, you're going to feel more. And of course, as you increase the magnitude, the intensity or more energy actually reach it, the ground motion is stronger. But what's interesting is what happens here. That at 1 kilometer, if we start with magnitude 3 and increase to magnitude 5, we get more and more and more energy. But at some point there's an energy saturation. So really there's a magnitude saturation beyond a specific magnitude threshold. It doesn't matter anymore, just a second, if you're at a magnitude 7 or 8. Yes?
So this is all, horizontal acceleration, not vertical?
Yes, thank you. This is all horizontal acceleration. There's no vertical component here. There's actually 5 papers coming up with the vertical component separately. So the vertical component is treated as separate models. Some of them are very similar to the horizontal with just different coefficients, and some are a little bit different. But we're having a much harder time with the vertical component. It's a lot more also influenced from surface waves, more than the horizontal component, so there's a lot more going on. But if I go back here, so I have increase in magnitude, increase in energy, I feel stronger ground motion, but beyond a certain magnitude, it doesn't matter anymore. And this is what these models have shown. I mean, you can see that in the older model over here as well. But the nice explanation actually came from Baltai and Hanks. This is Tom Hanks, very well-known seismologist, geologist, seismologist, and they, from the USGS, they followed the NGA and kind of in a parallel project tried to explain. So they have a paper called, I don't remember the exact title, but something like Explaining the NGA Project. So they take the NGA project, which is very engineering oriented, and then try and break it into components and explain it from a very seismological, physical point of view. And specifically this component of the magnitude saturation, they say, look, you have a rupture. If you're very close, and in this case 10 kilometers from the rupture, this is the amount of energy you're going to feel from this patch size L. If you increase the patch, and usually as the magnitude is bigger, that means the rupture has to be physically bigger, and at some point it becomes longer, not bigger in depth, but just longer. So if you just increase the length of this patch, this site over here is not going to know about it, because it really only gets most of its energy from this patch over here. So this is the very simple physical explanation of why we see in the data the magnitude saturation, and really the ground motion record close in at a short distance from a magnitude 7 and a magnitude 8 are almost the same ground motion, or the same ground motion on average.
And tell me, why would it be 1G?
Why would it be 1G? That's what the data shows. That's not, this is 1G, this is not PGA. So now if you look at the details, it does matter, because the response spectra peaks at 0.2 seconds. So the PGA is going to be lower. This is the peak of the response spectra, and the 1G is at magnitude 8, 1 kilometer from magnitude 8. It's going to be very strong.
Yeah, I was asking why is it?
Why is it around? It's actually not around 1G. It's a 1 point something. It's not 1.
Okay.
It's 1 kilometer and it's a 1 point something G. And that's what the data shows. Another thing, so magnitude saturation at short distances is what we get from the data, and we can explain it with physical supplementing, kind of a physical approach. Not simulations, but just trying to understand it from other physical theories, like point source spectrum. The big difference here, by the way, if you look at the details, the big difference between the model in 2008 and the new model in 2014 at small magnitudes, you can see big difference at all the distances, is because the 2008 database didn't have small magnitudes. The magnitudes only went down to a magnitude 4.5 or 5. So, but people still used it to lower magnitudes, and one example is what was done here in the building code, but everywhere around the world, people still used it outside of the data that was used to build the model. And when people extrapolated the functional form, they went all the way to here. So at a magnitude 3, 1 kilometer, they would predict 0.1 G. But when you put in all that small magnitude earthquakes into the database, you see that there's a break in the slope here, and really, these small magnitudes have much, much lower energy. So making that database bigger and extending it to other ranges of information is important, even if most seismic hazard analysis don't really care about a magnitude 3. But to predict well the 4.5 and 5, you need the 3, if you understand what I mean, to get this slope. So this was the magnitude scaling. I'll continue to the distance scaling. If I look, and again, there's a lot of different lines in this plot, but you can just focus on the solid lines, ignore the 2008 model, and look at the solid lines. So I have, again, the rupture distance. This should be in units of G at spectral acceleration of 0.2 seconds. And again, at very short distances, the large magnitudes, we have the same saturation we had before, and we have different slopes. If you look at the magenta line and the red line and the green lines, they have slightly different slopes, so slightly different distance scalings as a function of magnitude. Whereas if I look at the older models in the 90s, they had the exact same slope. So all these lines are parallel, meaning there's a distance scaling. I know my ground motion will become lower at distance, but it doesn't matter what magnitude it is. Well, the data shows that it does matter what magnitude it is, and guess what? If you put in a magnitude-dependent distance scaling, your functional form becomes longer and more complicated, more if statements if you do any coding. So, yeah, the functional form becomes more complicated, but if you see that in the data, you want to be able to describe it in the model. And this is what it shows. So we see a magnitude-dependent distance scaling. What we also see is, this is showing all the data, but when we looked specifically at the at least three regions where we had most of our data from were California, Japan, Taiwan, and China, but China was one event, Wenchuan. If you remember, there was a big earthquake in China in 2010? Eight? Okay. Time flies when you have fun. So we looked at, so the bold line is just everything, and then we separate it to Taiwan, China, and Japan, and you see different scaling, especially when you pass around 80 kilometers. So what happens is, at short distances, or out to 80 kilometers, plus or minus 50, 80, the energy radiates kind of geometrically. So you have geometrical spreading. The energy attenuates as a function of the distance, mostly. Beyond that, it's going to be a function of what the crust looks like, the materials in the crust, the Q, if you've had a seismology course, so how much energy is released in the crust, and that is going to be different between different parts of the world. So yeah, we can build a big database with all these different ground motions from around the world, but we can also today regionalize that and look at different response from different regions because we have enough information from these different regions. So we have regionalized long distance attenuation. We also have regionalized site response, but I think I'm not going to get into that unless someone asks for it. And we have a magnitude dependent rate of attenuation, so distance scaling. So all these different components, again, kind of added into the newer updates of the models. So that was the basic, magnitude and distance scaling. I'm going to maybe a little bit more quickly talk about the hanging wall effect because I think it's interesting because that's where we really only have At 2008, in the NGA1 project, we really only had 2 events where we actually had recordings on the hanging wall. This is Chi-Chi in Taiwan, 1999. So this is the fault, and these are the recordings, and you can see the recordings on the footwall and the recordings on the hanging wall, and you can see a clear difference. And this is Northridge, this is the fault, it's buried, and I don't know, maybe some of you can see a difference, some can't. This is harder to tell, but only 2 events. So if you do an empirical model, meaning you do regression on recordings, and you only have 2 events, one shows dependence on hanging wall, one doesn't, what do you do in your model? And this is really how the NGA West 1, the models in 2008, this is how they looked. And there's a lot of scatter above the hanging wall, because this all looks the same. But then over here, it depends what the modeler decided to put in. The data doesn't show enough. So what they decided to do in NGA West 2 was run simulations. So in this case, they ran 34 3D finite fault simulation of reverse faults. This is the range of magnitude and distance, and some of them reached to the surface and some didn't. This is how the rupture looks like. So this is the slip distribution on the rupture. You can see it's very patchy and heterogeneous, but this is more realistic than making it smooth and nice. This is what real ruptures look like, and this is based on, should have written here, the finite fault model is based on Graves and Pitarka. If you have heard the names, they developed the framework, and then Jennifer Donahue and Norm Abrahamson used that to run 34 different simulations. This is how the map view of this simulation looks like. This is where the fault is, and all the blue dots are stations. So we locate all these different stations around the fault, record the time histories, and now we have a physically based numerical or theoretical data set of how the ground motions are going to behave if we believe their framework, and we can describe how that will behave on the footwall, 12 kilometers left of the fault in this case, and 12 kilometers, same distance, above the fault. I believe this could be maybe these 2 dots. I'm not sure. Yeah, probably these 2 dots. And you can see a clear difference. So based on a lot of time histories like these, they developed their own little GMP just on the hanging wall. And they have the model that describes, I don't have it here, the GMP just for the hanging wall. And then they offer that as a component to the larger NGA GMP developers as one component in the long equation. Say, take it or leave it. You can use it or not. It's up to you. But here's a specific model for the hanging wall. And ASK13 adopted that. And you can see, actually, these are, again, the different GMPs, the NGA West 2 GMPs on the footwall and on the hanging wall. There's still a big scatter, even though there's physical numeric, but some people decided to use it and some didn't. Clearly, if you track this line of Idris, again, he chose not to use this component, as his model looks a little bit different than others. And others, if you look at ASK, the bold line, have a smooth transformation. This is the fault. So above the fault, it grows larger. There's more energy as you're above the fault above the hanging wall. Right above the fault, you get all the energy, and then slowly it goes back down. And the way to test if our model works or doesn't, the only way we know if we run an empirical model is to look at residuals. So we take the actual data we have minus what the model would predict, and we call that a residual. And to know if it works or not, we would like our residuals to have zero bias, so be right centered on the zero, and not have a trend and not have a bias. So that's the way we test an empirical model. And if I look at the residuals as a function of distance, magnitude, and dip, they're pretty good. I mean, maybe you could say it goes down a little bit here, but they're pretty good. And again, specifically for ASK14. So this is how the hanging wall model, this is how like this type of hybrid model works, of basing one component based on simulations and bringing it in to the larger empirical model. That's the concept. So, no, sorry, I was going to skip this, just a minute. So in summary, repeating what I said a few slides ago, the physical phenomena try and predict what my structure is going to feel, what type of ground motions I'm going to feel from any type of earthquake, anywhere around me, at any distance, any mechanism, is very complex. People are trying to do that numerically, but there's still, it's still not exactly ready to be used in engineering applications. Maybe one day it will be, not yet. So still we need to look at empirical models. We have a big database, it's new, and that means we also have a complicated functional form because we try and bring all these different aspects into the functional form. There are large uncertainties where we don't have enough data, like, for example, above a hanging wall. So we, for example, large magnitudes, short distances, hanging wall, and hence we supplement that with simulations for specific components, like I just showed you briefly. In Israel today, this is what our seismic hazard, national seismic hazard map looks like. The building codes, the recent one uses Campbell and Bazornia 2008, so the same Campbell and Bazornia had a new update in 2014. Our building code still uses the 2008 equation. That's okay, it can be updated sometime in the future. But why use an empirical model from California and nothing from Israel? Well, first of all, we don't have enough data to create an empirical model. We can say, Baruch Hashem for that, or thank you, or whoever, thank you, but we don't have a lot of data, of earthquake data, to build an empirical model, and that's why we need to use knowledge that was based somewhere else. But, and we also don't have a lot of information on the sources and earthquake sources and crust to really develop valid, strong theoretical and numerical models. But we could obtain more data, like just put more stations on different, more varied site conditions, for example, and that is slowly done, and the instruments are getting a little bit better, although it's still a little hard to get the data. And another thing that could be done, and is actually, we just got a grant to do it, is to try and develop a new GMP for Israel by combining local data, what we have, which is mostly small magnitudes, and kind of tying it together with large magnitude knowledge we have from other places in the world. Again, a hybrid solution of having what you have and then adding in components from other places in the world, for example. That's it for today. I'll be happy to take any questions.
Thank you very much. Any questions, please? Okay.
It's not specific on the talk itself, but you mentioned the Tafyud 413 side. So that's 2013, right? Did the new one something like this? And from what I remember,
so, yeah.
It's a great improvement on the one that was before, putting in some other elements such as the soil types and stuff like this, which weren't very abundant. But do you think that using these kind of equations and generalization like the 413 is enough, or would you recommend making a specific site survey for each site that you're building on? I mean, here in Israel
You're
now.
talking specifically about the site response component. So even if you do a site-specific survey, you have it. That's okay. You can test the exact soils in the site. You can do a borehole, pay hundreds of thousands of shekels or whatever to know the exact specific conditions in the site. And you have to do that for an important structure like a bridge or a hospital, or you won't do that for any just residential building.
The site-specific also includes acceleration, no?
But exactly, to do a site-specific response, you have to still evaluate what the rock is going to feel, and then multiply that by the site response. So you have to still use either a GMP or a numerical platform or something, or the standard to tell you, so the standard, what the standard says is, what the map says is, this is what you're going to feel on rock. This still says, in the report, there's guidelines what to do when you're on different types of soil or different types of site.
013.
But this is specifically for rock. It's not exactly rock. In California, it's rock. It's VS30 of 760. In Israel, that's not really considered rock. That's a whole other issue, which we're also looking at right now. But this specifically uses the GMPs, uses a big probabilistic framework to calculate what every point on the map would feel from what's the hazard from different sources and different probability of exceedance, a specific ground motion level. So if you're an engineering of a simple building, you would go here in Tel Aviv and say, oh, my ground motion is going to be 0.1 G. And I put that into my structure, do a pseudo-static analysis, and that's what the ground motion is going to be, or maybe multiply it by the site response. And if you want, you can know the exact conditions of the site and add that, but you still have to know what the motion is going to be on rock. We still need a GMP to do that.
Okay, Uri?
Did you use any of the nuclear verification explosions to try and get better attenuation models for Israel? Because it is indeed very different than in California. It should not behave like California.
In Israel, haven't done yet any work. We just got the okay on the grant. So, I don't know. We might use it for, you mean for just the wave attenuation, right? So in the GMP, there's a component on the probabilities of the different sources and all that, and that's where you have to separate out the explosions. But maybe to get the crustal response.
Yeah, because that's what I mean. The structure is both the crustal and the.
But that would give very small magnitude response, right? The explosions are equivalent to.
Were several tons explosions.
Okay.
They did. I mean, so.
That's a good idea. I didn't really. I didn't think about that, but we might put it in. Yeah, we might bring it in. I'd be happy to hear more of what you know about that.
Okay.
You said that you're going for Israel to use the information that is available and used for large earthquake evidence from outside of Israel. What about paleo earthquakes? I know there are limitations for using geological records, but with the limitations, are you thinking of trying to get the information on large earthquakes from the geological?
I think the information from paleo earthquakes can come in as constraints on activity rates. So more on, not on the GMP, but on how the slip rate or the probability of a certain earthquake to happen on this fault or this fault. How often do earthquakes happen on specific faults? That's not in the GMP. The GMP, it's very hard to use paleo information or historical earthquakes because you don't really have a value. So if we take even intensity, even Jericho, which has the most information that we have, right? And intensity, still to move from intensity to actual ground motion information, spectral acceleration, there's such a huge uncertainty there that I don't think we're going to want to put that uncertainty into the equation. It would definitely be good, though, to maybe use that as a validation. So you can build the model and then use that information to test if it agrees. Maybe that's more better approach, I think.